someone can someone tell me what's different between marginal distribution and conditional distribution? In the sense that you understand, there's no formal definition. Yeah.
Conditional, I know we use like percentages, they were more like specific.
Yeah, more specific, right? When I ask you to do conditional distribution is more detail oriented, right? Where marginal distribution is you only have two distributions, right? Men versus women, gamer versus non-gamer. Now, the reason I introduced those two types of distribution because today we're going to talk about Simpson paradox. By the way, it has nothing to do with the show. The Simpson paradox is study the effect of the lurking variable or the confounding variable and how is affect the relationship between two categorical variable. Right? So the effect of lurking variable that changes or reverses the relationship between two categorical variables is called the Simpson paradox. So that means your marginal distribution tell you one thing, and then your conditional distribution tell you other things. Right? So that means that's paradox, right? They're not consistent. And why is that? Because of the lurking variable. And that's called the Simpson paradox. Okay. So what I just said, that's the bullet point number 2. The Simpson paradox occurs when the direction of the relationship is reversed within subgroups compare. When I say subgroup, I meant conditional distribution, detail oriented, compares to the direction of the relationship within the total group. So they have two different results, and that because of the confounding or lurking variable. For the exam, I suggest you understand, or at least know this definition in context, of course. Oops, too dark. What are the two categorical variables? Right? You have to put it in context. A lot of time, a lot of you lose your point because you didn't put your sentence in context. Example, let's take an example of helicopter save lives. Let's compare the percentage of accident victims who die with helicopter evacuation and with usual transport to the hospital by road. So if you look at the table right there, the number of people who die while having helicopter transport is 64 out of 200. So let me calculate that distribution. So 64 divided by 100. 200, I'm sorry, 200. 64 divided by 200 is 32%. And then for the road transportation is 260 out of 1100 is roughly 24%. And what are this kind of distribution here? Conditional or marginal? Marginal, right? It's marginal. Right? Now, does it bother you? Does it bother you a little bit? It seems like people tend to die while having a helicopter transportation as opposed to road. I thought with having helicopter transportation would be better. You get to the hospital quicker. There's no traffic to worry about. But why is that? Well, let's take a look. Let's take a look a little closer to why that is. Let's take a look at the seriousness of the accidents. Right? Usually, when you require helicopter transportation, because of the severeness of the accident, right? You need to get to the hospital as soon as possible, as opposed to the regular road transport. So let's take a look at the percentage die here with helicopter. 48 divided by 100 Well, that's 48%, right? Then with versus road transportation, 60 divided by 100, 60%. So with the severe, when you have a very severe accidents, the percentage of people who die using road transportation is larger than helicopters. So now it makes sense, right? Now things make sense. But why do we have the result up here? Why do we have the result up here? Well, the reason we have the result in the marginal distribution because the seriousness, right? That's your lurking variable. That's your confounding variable, right? Like I said in the beginning, people who in critical condition require helicopter, right? So they tend to have a higher chance of dying on the way, right? As opposed to using road transportation, moderate to mild condition. Right there. So that's the explanation. So that's the serious accident. Let's take a look at the less serious accident. So less serious accident, I have 16 out of 100 die. So that's 16%. I'm talking about the death rate here, right? And then for road, 200 out of 1,000, that's 20%. So when I look closely to the data, I see the result is that people who use a helicopter the death rate using the death rate for using road transportation is larger than helicopter transportation, right? As opposed to when I use a marginal distribution, the result is opposite. So that's Simpson paradox, right? We have two different results. They contradict each other. And because of the lurking variable. And what is the lurking variable here? What affect that differences? We just talk about it. Seriousness, right? The level of seriousness. So seriousness is the lurking variable that responsible for the contradiction between subgroups versus total group. Let's say distribution, I meant percentage here. Usually the lurking variable in Simpson paradox is categorical variable. So if you look at the marginal distribution, your observed association can be misleading because they're present of the confounding variable or looking variable. So one more sentence. The observed association. What do I mean by association? Association between what and what? I you gotta understand every single word in there, right? Let me finish writing and I'll ask you, can be misleading. Misleading when there are lurking variable. By the way, you don't hear lurking variable very often in the textbook. You hear confounding variable. I like to use the word lurking because it's kind of give you a caution. Right? That's not your explanatory nor response. What is the association? What is the association that I'm talking about here? Your answer is in the, it's already there. Association between subgroup and the total group, right? That's what it meant by misleading. And of course, you have to put in context. All right, so that's the helicopter example. Let's do one more example, and this time we're gonna use Google Sheet. On your exam, I'll let you use your computer. Just use Google Sheet. If you're not comfortable with it, you can use your calculator. Field goal shooting. Here are the data on field goal shooting for two members of University of Michigan in 2017 and 2018 men's basketball team. This is actually real data from school. I got. They're Charles, Matthew, and Duncan Robinsons. 2-pointers, or sometimes they call it 2 shots. There's made and miss, and then 3-pointers or 3 shots made and missed by both basketball players. What is the percentage of all field goal attempts did Charles Matthews make? Right, so we talk about the make here, the May one. So of Matthew. So let's say Matthew. You know, I'm gonna say Charles is shorter. One thing you should know about mathematicians, they're very lazy. That's where the notation come from. Right? Charles. All right, so can someone tell me percent of Charles made? So this is made. I'm not talking about missed. Right? Will be equal to what? To the main column, right? The main column is right there. Right? 2 shot, and 3 shot. So 171 plus 34 divided by all of it of Matthew table. Right? So all of it will be 171 plus 34 plus 136 plus 73. That's all of it. One 171 plus 34 divided by 171 plus 34 plus 136 plus 73. Roughly 4.495. I'm probably gonna say roughly 50%. No, let's just say 49.5. So, and then for Duncan Robinson, he made what? May column will be 44 plus 78 divided by all of his. So 44 plus 78 plus 30 plus 125. Roughly 44%. So who have better shot? Chars, right? It look like it, at least in the first glance, char have a better shot. Anybody here watch basketball? No? Now, so that's marginal distribution. Remember, this is marginal distribution. Those are marginal distribution. Now, find the percentage of all 2-point field goals and all 3-point field goals that Charles made, and then do the same for Duncan. This is a bit more detail oriented, right? So this must be conditional distribution. How do I know? Because as for marginal distribution is only 2 percentages. For this, you're gonna have more than 2. Right? We're gonna do this in, unless you want to do by hand, that's fine. So click on the data set. Me, I just go to my Google account. Make a copy of that. I put down the percentage that we did in part 8. Percentage of all 2-point, all 3-point. All right, all 2-point. Made. We talk about made here, right? Made, not missed. So equal. So made for 2-point made is 171. You can click on that cell and then divide it by all the true shot. All the true shot for Matthew is what? Should it be Matthew up here? I don't know why it's missing. Hang on, let me fix this. There's Matthew here as well, or Char, for that matter. So equal 171, which is that D2 there divided by the total of 2-point shot, or 2 shot, right? Which is here, 171. I think I can just click on that again. And then plus that, right, plus the 136. I'm gonna round it because I don't like it like that. There's more than a way to do this. So let's round first. Let's round first. Put the parenthesis there, and then comma, right at the end, comma. I'm gonna round to 4 decimal places because this is decimal. And I'll tell you why I'm doing that, not 2. Because when I multiply by 100, now give me yeah, that's it. That's all I need. That's all I need. I think in last lecture, I rounded last, which is the same thing. Which is the same thing. You can do that too. You can multiply by 100 first, and then round it to 2 decimal. Or you can round it to 4 decimal and then multiply by 100. And then you do the same thing for Matthew 3 shot. So equal 3 shot made by Matthew will be 34 here, divided by the total of all 3 shot. Let's see, which is 34, also 34, plus 73. I'll just click on the cell. Again, I'm gonna round this. One more parenthesis in the front here. Comma 4. That times 100. I want you to do the same for Duncan. I want to walk around and see how you do. Parentheses makes difference. When you divide something that more than one numbers, the parentheses around that. Things stay there for a long time. What else are you? I don't know. You would think, right? But maybe not because it's student. There's a lot of people with like non-geometric campus. There was one time I left my phone on top of my car. I took it out, put it on top of my car, to pull out other things. I left it 2 hours. I come back, it's still there. I was so nervous, like I'm not gonna go to the police station and see if anybody returned. But let me check my car first. It was still there. Impressive. Any question for me? Did you be able to figure it out? Well, what do you have for Duncan two shot? Yeah, three shot. Anybody else? Three shot for Duncan? No, don't be afraid. Yeah. Okay, sounds good because I'm expecting it to be larger than that. So that I can show you the Simpson paradox. So equal two shot Robinson's, which is Duncan, that divided by, make sure you put parentheses because the sum in the denominator. Yes. And 100. I'm lazy. Since I'm lazy, I'm gonna copy this. Should have done that in the last, and then paste there. And then all I have to change is what? Three shot is D8. D8 divided by D8 plus D7. Oh, D9. Plus D9. Thank you. There you go. You can just copy and copy over and change the cells. So what do you see here? Remember, part A, it looks like Matthew do better, right? 49% or roughly 50% versus 44. But if you look at within the two shot and the three shot, who do better? Lincoln, right? It is weird, right? How's it on the whole is Matthew better, and then within the pictures, Duncan did better. Before we answer that question, let's copy down the result first. Let me go back here. Oh, I'm so sorry, I didn't share the screen. I'm so sorry, I didn't share the screen. When you watch this, you won't see it. All right, sorry about that. You guys watch this later. You won't be able to see what I did, but you can just go to the data set everything's in there. It's everything I do is saved in there. So you come away, come back. So let me copy down the result using table. So I have Charles and I have Duncan. 2-pointer, 2-shot, and then 3-shot. What I did was take 171 divided by 171 plus 130. Was it 136, guy? Yeah, 136. And then the result is 55.7%. And then for Duncan will be 44 divided by the total of 44 plus 30. And then the result is 59.46%. For 3-shot, 34 divided by 34 plus 73, 32%. And then same thing, 38%. So Char has lower percentage for both type of field goals, but he had a better overall percentage. That sounds impossible. Explain carefully, referring to the data, how this can happen. Well, one thing you can tell me, Simpson paradox, right? So we can start out like this. We can say this is an example of the Simpson paradox. The comparison that holds for both field goal let's see, hang on, give me a second. When I say both field goal, I mean 2 shots or 3 shots. Field goal, field goal. Groups is reverse. Remember this characteristic of the Simpson paradox, the result reverse. Reverse when is combined into one group. That'll be part A. Remember, part A. There's one more thing. Now, there's one more thing. We know that it's Simpson paradox. We just don't know what is the lurking variable, right? In this case, we don't. You can make up things you want, but there's no way to prove the lurking variable. But if you look at the data set, what is the difference? Compare the 2-shot and the 3-shot made by Char, and then the 2-shot and 3-shot made by Duncan. What do you see? There's a big gap here. There's a big gap, right? Char had a lot of 2-shot, but not many 3-shot. For Duncan, it's more consistent, right? The number is close. The range is closer. So maybe that's one of the reasons why it changed the result. We don't know, but it's just, from the data set, we see that. So maybe, so you say notice jar has, say a large gap as you can see, a large gap for 2 shots. Large gap for 2 shots compared to Duncan. Sorry. Hopefully you can read my handwriting. I could have added another page like that. You can do it like that. You know, right? I could have added another page, but I want it to be in one page so that you can see the table and then talk about your result. Need that. All right, we're done. Then with chapter 6. Quiz time, like last time you turn yourself around.